Good afternoon, ladies and gentlemen, and thank you for attending my presentation. This is a preliminary study on a method which can be used to develop new applications. And on the way of this theory, we develop in the meanwhile further algorithms which will bring new improvements, especially in the quality control, in seismic processing and interpretation, and in seismic petrophysics and rock physics integration. The title of the presentation is Neural Convolutional Seismic Amplitude Attribute Conv44A, Enhancing Structural Resolution. The name Conv44A will specify that the algorithm for the calculation of this attribute is developed within the hidden layer 4 of the block 4 of a VGG19 neural network, which is situated here in this position. VGG19 is a variant of a VGG model, which in short consists of 19 layers (16 convolutional layers) (5 max pool, 1, 2, 3, 4, 5), 3 fully connected layers, and 1 softmax. Let's go on with the starting motivation. There is a parallelism in the visual perception theory, computer vision, and 3D seismic imaging and seismic attribute analysis. Imagine a zero perception universe where we just could see one color of a certain frequency or no color at all. We could develop no knowledge there, no memory, and even no intuition of the universe where we now live. In our universe, the visual perception is marked by what we call in machine learning decision boundaries, dividing one visible frequency from the other in classification, and edges in convolutional neural networks. In 3D seismic attribute analysis, we call these boundaries singularities. In classification or mapping, they mark seismic attributes transitions. Let's go on with the parallelism in deep learning and seismic attribute analysis considerations. We can go through the slide in the vertical direction and analyze each column in the vertical direction. Or we can go through the slide in the horizontal direction and analyze each row in the horizontal direction. In the vertical direction, images represent processes in one single discipline. We have machine learning, deep learning, we have seismic attribute analysis, process inversion interpretation. We have linear and nonlinear decision boundaries, and we have simple and complex structures. We have an increase in structural and algorithm complexity as we go from the upper position to the lower direction. Linear decision boundaries, simple structures, nonlinear decision boundaries, complex structures. Algorithm examples in deep learning, for instance for linear boundaries, we have that linear decision boundaries can be solved by logistic regression, linear support vector machines, simple activation function, sigmoid logistic regressions. For nonlinear decision boundaries, we have that linear decision boundaries can be solved by complex algorithms, neural networks, density connected neural networks, convolutional neural networks, and recurrent neural networks, hybrid neural networks. As far as Seismic is concerned, simple structures, example of processing and inversion algorithms are post-stack time migration, post-stack inversion. And for complex structures, example of processing and inversion algorithms are pre-stack depth migration, reverse time migration, full wave inversion, pre-stack inversion, simultaneous elastic inversion. The future trend to solve for processing and inversion problems in 3D seismic will be to use new architectures of hybrid and complex neural networks. Now we continue with the consideration of singularity parallelism. The zero perception universe lacks of singularities. In seismic, singularity detection is used in interpretation both for mapping in the vertical direction and in the horizontal direction. The parallelism concept of singularity in convolutional neural networks is reflected from the EAGE concept. In convolutional neural networks, we extract information from the receptive field. In 3D seismic, from the reflector beam with its fold dataset. In seismic attribute analysis, we parameterize singularities with a Holder exponent H. In convolutional neural networks, with the activations computed from the kernels. The great property of a convolutional neural network is the capacity of capturing and enhancing these singularities information while evolving from the low-level features captured within the shallow layers and the higher-level features captured within the deeper layers. Now we consider the expression of singularities in seismic attributes. Singularities are seismic attributes. How do we extract attributes in 3D seismic? Let's consider amplitude attributes. One theory which gave an impulse to the development of seismic attributes analysis was the application of the Hilbert transform to the real seismic trace in the real plane to produce the complex trace in the complex plane. This theory was introduced by Tanner et alias in 1977. This gave rise to further attributes which are also extensively used in linear attributes analysis and in neural network applications. Hampshire-Russell were among the first to apply complex amplitude attributes as features in dense connected neural networks to compute missing logs or other seismic attributes to distribute across the seismic volume. Instantaneous frequency is calculated from the instantaneous phase, and many other instantaneous attributes are calculated from the instantaneous frequency and the instantaneous phase. Here we have the example of a missing log calculated from 3 feature attributes. Here we have the example of a P wave derived from 4 feature attributes and then distributed into the 3D seismic volume. To this point, we analyzed ways to extract seismic attributes from wave traces. There are many ways to create wave features that can be further processed to compute seismic attributes useful for interpretation. This is the main topic in this presentation. We analyze now the schematic of program implementation for Conv44A attributes. The code was implemented in TensorFlow and Keras. After all previous considerations, it was logical to try to apply convnets to extract attributes from seismic data and study the parameterization of this data through a convnet. In this program implementation, 2 sorted amplitude maps, struct1 and struct2, of the area and 1 white noise amplitude map, target G, are input into the VGG19. During the optimization process, the target map G activations at Conv44 are in parallel steps updated from the activation of struct1 and struct2 at Conv44. 3 cost functions are calculated. Cost struct1g, that we call in the implementation JStruct1, updates the activation difference at Conv44 across channels. Cost struct2g, that in the implementation is called JStruct2, updates the cross-covariance difference of activations of struct2 and G across channels at Conv44. A third cost function is the total cost and is the sum of cost struct1g and cost struct2g. The total cost after optimization produce the final target map G, which is the enhanced structure resolution of the input maps struct1 and struct2. This is the detailed schematic of pre-trained VGG optimization process. During the optimization process, the target map G activations at Conv44 are in parallel steps updated from the activation of struct1 and struct2 at the hidden layer of Conv44. Cost struct1g update activation difference from struct1 and G at Conv44 across channels. Cost struct2g update cross-covariance difference from struct2 and G at Conv44 across channels. This is the cost function JStruct1. This is the normalization factor. These are the activations of struct 1 and target G at conv4 element-wise subtracted and squared. This is the cost function J struct 2. This is normalization factor. This is the unnormalized cross-covariance matrix that is calculated across channels for struct 2 activations. This is the unnormalized cross-covariance matrix that is calculated across channels for target G activations. Subsequently, the cross-covariance matrices G2 and GG of struct 2 and G at conv4 are element-wise subtracted and squared. This is the total cost function Jg. It is the normalized sum of J struct 1 and J struct 2. These are the normalization factor alpha and beta. Beta is set at 90% struct 2 contribution. Alpha is set at 10% of struct 1 contribution. 90% struct 2 contribution means that this term is responsible for enhanced resolution in the final map. Shortly, some considerations on the optimization process with the ADAM adaptive learning rate optimization algorithm. The ADAM algorithm calculates the exponentially weighted averages EWA VDW VDB of the gradients DW and DB. This is DW, and DB should have a delta B here and here. The second step will consist in using this weighted average after multiplication for the learning rate alpha, not to confuse with the hyperparameters used in the total cost function, to update the gradients dW, dB during gradient descent, and then calculate the parameters W, B, weight and bias. A bias correction term 1 minus beta exponent T, time constant, is used to compensate for the initial part of the weighted average which start at two lower values. Finally, the ADAM algorithm, optimization algorithm, is calculated from the component of the momentum. This is the component of the momentum corrected, and the component of the RMS prop. This is the component of the RMS prop corrected for the learning rate alpha to calculate the parameters. Finally, I came to the conclusions that applying this method, an enhanced resolution observed compared to the input images combined. The final map shows an improved enhanced resolution compared to the input maps struct 1 and struct 2, and even improved resolution filtered with a directional filter compared with the filtered version of the original input maps. In the end, I wish to thank the EAGE for organizing this event, and thank you again for your attention. For any question, you are welcome to contact me at the email address below.